Well, thank you very much, Michael. Thank you very much to the organizers for inviting me, giving me the opportunity to speak here. And also thank you very much to the ESI. It's always a pleasure to being here in this wonderful and inspiring atmosphere. Yeah, I'm speaking about approximation in weighted Korobov spaces. The results that I'm going to present come from joint works with Adrian Ebert, who was formerly in Linz and now moved to industry, and Peter Kritzer, who is in the audience here also. So approximation in weighted Korobov spaces is a topic that has long been considered in a lot of papers. Let me first introduce the function space setting. I think does not work. No. It's off. That it cannot work. Thank you. With the best trick to put it on first. Let me introduce the function space setting. So we are considering weighted Korobov spaces. Weighted Korobov space is a reproducing kernel Hilbert space depending on 3 parameters. D is always the dimension of the underlying space 0, 1 to the D. Alpha and gamma are 2 parameters. I will say a bit more on this later on. And the reproducing kernel of the weighted Korobov space is given by this series expansion here, involving certain coefficients R of k depending on D, alpha, and gamma. And the corresponding inner product is given by this series you can see here, with here the reciprocal of the RK functions, and also the Fourier coefficients of f and g are involved. Now the growth rate of these functions Rk, or the decay rate of the 1 over Rk, describes the decay rate of the Fourier coefficients of the functions from the Korobov space, and therefore are related to the smoothness of the functions from the space. And in our setting here, we consider finite smoothness, which is described with the parameter alpha. Our coefficients Rk are of product form, are alpha gamma j kj, where kj is the j coordinate of k, and for some alpha bigger than 1 and some generic weight gamma, the alpha gamma k are defined being 1 if k is 0, and gamma over absolute value k to the alpha if k is different from 0. So this alpha here describes the smoothness of the functions from the Korobov space, and therefore it's always often called the smoothness parameter of the space. And what are these gammas? The gammas are so-called weights. We are considering the weighted setting. The weights are introduced in order to model different importance of coordinate directions of the functions, an idea going back to Henryk Wozniakowski and Ian Sloan introduced such weights the first time in the 1990s. And since then, weighted spaces are very often considered also weighted discrepancies in discrepancy theory and so on.
With J, you could imagine that too, right?
Yes, could be considered too here, but not in my setting here. Alpha is a fixed parameter, and also gamma, the weight sequence, is given and fixed. Yeah, these Korobov spaces are important reference spaces for quasi-Monte Carlo rules, especially for lattice rules, and they are very often considered in the context of numerical integration, but also in the context of approximation theory. Yeah, we are studying LP approximation. For the moment, for P either 2 or infinity, that is, we consider the embedding operator, I call it app here, from the weighted Korobov space to the LP space. And in order to approximate this operator with respect to the LP norm, it's well known from general theory that it suffices to employ a linear algorithm in order to achieve the best results. The linear algorithm is of the special form you can see here, denoted by E and D. D refers to the dimension, N the number of information evaluations. Here the functions Gi are from the LP space, and the Ti are bounded linear functionals on the Korobov space, and we assume that they belong or come from some permissible class of information. So this result, that it suffices to consider linear algorithms only, is a result of Bakwalov from 1971. Yeah, and we assume that these information evaluations belong to some permissible class of information. And in the first place, we consider the information class lambda all, consisting of all bounded linear functionals on the Korobov space. And in the second place, we consider the class which is called lambda standard, which consists of all function evaluations only. So we are speaking here about reproducing kernel Hilbert space, and this also, of course, implies that function evaluations are bounded linear functionals, and therefore the class lambda standard is a subclass of the lambda all class. Yeah, we considering the worst case setting here for our error analysis, and as a reference, we introduce the so-called initial error, which is obtained when we approximate the function f by 0. The initial error denoted by E0 of the approximation problem, and this is just the norm of the embedding operator, and in this present case here, this norm can be easily computed. If in the case of L2 approximation, the initial error is just 1. And in the case of L infinity approximation, the initial error is given by this product. So the square root of this product, zeta alpha, is the Riemann zeta function. Alpha is assumed to be bigger than 1. So this is a finite number. And here the weights gamma j are involved. So there is a difference between these two problems already for the initial error. In the case of L infinity approximation, the initial error is strictly bigger than 1 always. And even more, depending on the weights, it could be that the initial error depends exponentially fast on the dimension. So grows exponentially fast in the dimension. So this is the initial error. And the worst case error now of an algorithm using n information evaluations is just the supremum of the LP norm of the error. So functional of f minus algorithm, and the supremum is extended over the unit ball of our function space of the weighted Korobov space. Yeah, and being interested in the smallest worst case error we can achieve with a given number of information evaluations, we also introduce what we call the nth minimal worst case error with respect to a given class of information, capital lambda, which is the infimum of the worst case error of an algorithm using n information evaluations from the class capital lambda. This is the nth minimal worst case error we are interested in. And in the next step, in the last step, we introduce somehow the inverse of this nth minimal worst case error, the so-called information complexity, which depends on some error threshold epsilon between 0 and 1, and d the dimension. And the information complexity is just the minimal number n of information evaluations that is necessary in order to achieve an nth minimal error of at most epsilon times some error criterion. And for the error criterion, often the following two choices are considered. First one, where the criterion is 1. One speaks about the absolute error criterion. So in this case, we want to have the end minimal error at most epsilon. For the information complexity, we indicate this sometimes by adding the subscript apps to the notation. And the second error criterion that is considered is the so-called normalized error criterion, where this criterion here is said to be the initial error. So in this case, we want to reduce the initial error by a factor of epsilon with information evaluations. Maybe some remarks on these definitions. First, for the L2 approximation problem, the initial error is exactly 1, so the normalized and the absolute error criterion coincide, and we have this relation, so it's sufficient to consider one of those. For the L infinity approximation problem, the initial error is strictly bigger than 1, so this, of course, implies that the information complexity with respect to the normalized error criterion is dominated by the information complexity with respect to the absolute error criterion. And there's also the relation between the two problems. Of course, L2 approximation is not harder than L infinity approximation, which means that the information complexity for the L2 approximation problem is dominated by the information complexity for the L infinity approximation problem with respect to the absolute error criterion. Yeah, for the information class lambda all, which is often used as some kind of reference, there is a nice way expressing these information complexities by means of eigenvalues of a certain operator, namely of this operator WD here is the approximation operator concatenated with the joint approximation operator from the Korobov space to the Korobov space, and assume we have the eigenvalues of these operators in ordered in a non-increasing way. Then it is well known again from a general theory that for the L2 approximation problem with respect to the class lambda, all the information complexity is just the minimal index n such that the n plus first eigenvalue is less or equal epsilon square. And a similar result holds true for the L infinity approximation problem, where the information complexity is just the minimal index n, such that this sum here of the eigenvalues starting from the n plus first is less or equal epsilon square times the considered error criterion. Yeah, and if you have now this ordered eigenvalues, one can write down the information complexity and study these quantities. And yeah, for the particular problem we are considering here, the eigenvalues are well known. We have the eigenpairs of this operator, and the eigenvalues are exactly these coefficients that appear in the definition of the Korobov space. So this is also well known. And now, yeah, having these eigenpairs, we can use the theory. The only problem is, of course, that we do not know the ordering, because we need to order the eigenvalues in a non-increasing manner. And that's the problem here, of course, especially in the multidimensional case. And the problem is that here also the weights appear, and we do not know much about the weights. So the ordering here is the problem, but nevertheless, we can use this theory here to deduce interesting results on the information complexities with respect to the class lambda all. Yeah, and this is now our aim. We want to study the growth rate of the information complexity when the information when the error threshold epsilon goes to 0 and the dimension d goes to infinity. Okay, so if the information complexity grows exponentially fast in the dimension, one says the problem suffers from the curse of dimensionality. That's of course bad, the property that we do not want to have. And our aim is now to find conditions on the weights of the space, conditions on the gamma, such that this is avoided. And we want then to classify the growth rate of the information complexity when epsilon goes to 0 and d goes to infinity, with respect to the weights of the space. It's our aim. And the classification is done by several notions of so-called tractability. And that's what I'm going to introduce now. So we consider a sequence of approximation problems indexed by the dimension d for some information class capital lambda. And we say that these problems are polynomially tractable if the information complexity is bounded polynomially in 1 over epsilon and the dimension d. So this means polynomial tractability. And even more, if on the right-hand side we do not have any dependence on the dimension d here, then we speak about strong polynomial tractability. We say that the problems are strongly polynomially tractable if the information complexity is bounded polynomially in 1 over epsilon, but uniformly in the dimension d. Okay, so this is an even more demanding property. Of course, we are also interested in the smallest value tau here in the exponent of the 1 over epsilon, such that such a relation with a certain number c holds. And this exponent then is called the epsilon exponent of strong polynomial tractability. And I will refer to this also later on. So historically, these were the first two notions of tractability that have been introduced and starting already in the 1990s, again by Henryk Wozniakowski, Ian Slow, and Greg Wasilkowski and colleagues. Later then, in the run of the course of time, more and even more refined notions of tractabilities have been introduced to get a more concrete picture of the whole situation, how the information complexity grows. And one of the first notions that have been added then is the notion of weak tractability, which means that the logarithm of the information complexity divided by d plus epsilon to the minus 1 goes to 0 if the denominator here tends to infinity. So this notion of weak tractability means, in a sense, that the information complexity grows at a slower rate than exponential. That's just the meaning of this in a nutshell. Then later, the notion of quasi-polynomial tractability has been introduced, which means that the information complexity is bounded by some constant c times exponential of a parameter t times log d times log epsilon to the minus 1. Okay, so this means that the joke here. So the essence of this definition here is, which looks first sight maybe a bit complicated, that the information complexity is about epsilon to the minus t times log d, so that the exponent of the 1 over epsilon depends only weakly on the dimension d. That's the essence of this notion of quasi-polynomial tractability. And again, we are interested in the smallest value t that can be achieved here, the smallest value t, such that we can have such a bound for some constant c. And we call this quantity then the exponent of quasi-polynomial tractability. Further notions further notions of tractabilities are so-called sigma tau weak tractability, which is just an extension of weak tractability. Here with two additional parameters, sigma and tau, which are positive, and the sigma here appears at the exponent of d and the tau as the exponent of 1 over epsilon. And finally, uniform weak tractability, which means sigma tau weak tractability for all positive sigma and tau. So these are a lot of notions of tractability which are nowadays considered and studied in literature for different problems. Of course, here is a certain hierarchy in the tractability notions. Strong polynomial tractability implies a polynomial tractability, which in turn implies quasi-polynomial tractability. Quasi-polynomial tractability implies uniform weak tractability, and this in turn sigma tau weak tractability for all sigma and tau, and in particular, of course, the usual notion of weak tractability where sigma and tau are just said to be 1. And our aim now is to find conditions on the weight sequence in order to classify the one or other notion of tractability. This is also an old problem, also for L2 LP approximation. We consider here this problem has been studied since 20 years. First, for the primal tractability notions for polynomial and strong polynomial tractability, but later these new notions of tractabilities came up, and that's the reason why we revisited this problems and studied them again with respect to the more refined notions of tractabilities. Yeah, throughout we make some reasonable assumptions which help such that the formulation of the conditions are maybe not so technical. We assume throughout that the weights are ordered in a non-increasing way and are bounded always by 1. And we will use some figures of merit depending on the weights in order to give our characterizations. In first place, we will need the infimum of the weight sequence gamma j, and we will use this sum exponent S gamma, which is just the infimum of all positive exponents kappa, such that this sums here where the kappa appears in the exponent of the weights is finite. So, and we come to the first result for L2 approximation, and rather stating a theorem, put everything together in one table. So you have here a complete picture of the whole situation. For tractability of L2 approximation, remember, we do not need to distinguish here between normalized and absolute error criterion, but we have to distinguish between the information classes lambda all and lambda standard. All results here on the table are if and only if conditions. So we have really exact characterizations of the tractabilities. For lambda all, it's interesting that strong polynomial and polynomial tractability are in fact equivalent, and they hold if and only if the sum exponent is finite. And then also the newer notions of tractabilities are all equivalent again. Quasi-polynomial tractability down to weak tractability are equivalent, and any one of those holds if and only if the infimum of the weight sequence is strictly less than 1. There's no additional condition for this notion for sigma tau weak tractability if sigma is bigger than 1. So that's the case lambda all.
That means that the weight sequence does not need to go to 0.
Yeah.
Oh, okay.
Sufficient if you have one weight that is strictly less. So if you have, for example, 1, 1, and then 0.9, 0.9, then this was a bit surprising. For lambda standard, the situation is slightly different here. Strong polynomial tractability holds if and only if the weights are summable. So this, of course, implies that the sum exponent is less or equal to 1, this condition here. And here for a lambda standard, polynomial and quasi-polynomial tractability are equivalent and hold if and only if this lim sup here is finite. So we have 1 over log d, the sum of the gamma j from 1 to d. And we also have if and only if conditions for these notions of weak tractability. For example, weak tractability holds if and only if this limit relation here is satisfied, and similarly, sigma tau weak tractability for sigma less or equal than 1. We have here this, in addition, this exponent sigma, that's the difference here. And if this holds for all sigma between 0 and 1, we have the if and only if condition for uniform weak tractability. So also this tau here does not appear in the condition for tractability, for the weights. So for L2, for the L2 approximation problem, we have really a very clear picture of what's happening, how are the characterizations of the weight sequences in order to obtain the one or other notion of tractability, maybe some results, as already mentioned. The results for strong polynomial and polynomial tractability have been known before. For lambda all, the result was shown by Greg Wasilkowski and Henryk Wozniakowski in 1999, and for lambda standard by Erich Nowak, Ian Sloan, and Henryk Wozniakowski in 2004. All the remaining results are by Adrian Ebert and myself, published last year in the Journal of Complexity. And in case of strong polynomial tractability, even the exponent is known, denoted by tau star of lambda, lambda either the class lambda all or lambda standard, and it's just 2 times the maximum 1 over alpha, and again this sum exponent. So high smoothness and very fast converging weights to 0 imply a small epsilon exponent. And also for QPT, for quasi-polynomial tractability and lambda all, remember for lambda standard, this is not so interesting because then QPT, quasi-polynomial tractability, is equivalent to polynomial tractability. But for lambda all, also here the exponent, this t here, the smallest t that can be achieved is again of a similar form, with the difference that instead of the sum exponent, we have here 1 over log 1 over gamma.
Algorithm that deliver this. So for lambda all, this is obviously like projection onto the largest mode. But for lambda standard, what is the reconstruction operator?
For lambda standard, the construction is based on lattice rules. Essentially, it's just taking the Fourier series, cut it off at some place, and compute the Fourier coefficients with lattice rules. That's that in this case. Yeah, now we come to L infinity approximation. Here we require some more figure of merits, some further exponents, namely T gamma should be the infimum of positive kappa, such that this lim sup here is finite, where the kappa again appears here as exponent of the weights gamma j. And for every positive sigma, we define also the quantity u gamma sigma as the infimum of all kappa, such that this limit relation here holds, and again the kappa is here in the exponent of the weights gamma j. So, and with these figures of merit, we can again now state our result for L infinity approximation. Unfortunately, here we do not have such a clear picture like for the L2 approximation problem. Nevertheless, some results are available. So here, formally, we have to distinguish between the two error criterions, the absolute and the normalized error criterion. But here in the result, this does not matter. All result holds for both error criterions, for the absolute and the normalized error criterion. And all the results also hold simultaneously for the class lambda all and the class lambda standard. So now strong polynomial tractability holds if and only if the exponent S gamma is strictly less than 1. So remember, the condition for L2 approximation was that this exponent is finite. Here we require the exponent is strictly less than 1. Polynomial tractability holds if and only if this t parameter t of gamma is strictly less than 1. So these are the two if and only if conditions that are available at the moment. For QPT, unfortunately, we only have a necessary condition at the moment, namely that this lim sub here has to be finite. So here we only have the necessary condition, and also for the weak tractability notions, from weak tractability to uniform weak tractability, we only have necessary and sufficient conditions at the moment. For example, for weak tractability, it is necessary such that this limit here is 0, and it is sufficient if this parameter u gamma 1 is strictly less than 1. So these two conditions are very, very tight, but they are not matching, unfortunately, because the necessary condition, of course, implies that this u quantity here is strictly it's less or equal to 1. Okay? But nevertheless, we do not know if u equal to 1 is sufficient in order to guarantee weak tractability. So they are very close, but unfortunately not matching at the moment. But this is a gap that remains in the results that we have. Similar characterizations hold true for the other more refined notions of weak tractability, sigma tau weak tractability. Here we have this additional parameter sigma in our criterions, and also for uniform weak tractability, where the conditions have to hold for all sigma less or equal to 1. So again, a few results. Again, the results for strong polynomial and polynomial tractability have been known before by Francis Kuo, Greg Wasilkowski, and Henryk Wozniakowski, who proved this result for lambda all in 2008, for lambda standard by in 2009, and the remaining results are from a recent paper with Adrian, Ebert, and Peter. Yeah, as already mentioned, we only have so far a necessary condition for quasi-polynomial tractability, which is this condition here. And this condition, of course, implies that this parameter T gamma is less or equal to 1. And this is very, very close to the if and only if condition for polynomial tractability, which is that this T parameter is strictly less than 1. But nevertheless, at the moment, we cannot prove that these two notions are maybe equivalent, or the other way around. We cannot also not prove that T gamma equal to 1 is sufficient for quasi-polynomial tractability. So either one of these two possibilities holds true. And also, as already mentioned, the conditions for the weak tractability notions are very tight, but unfortunately not matching. A same gap in the conditions was observed for this problem by Erich Nowak and Henryk Wozniakowski, but they considered even more general weights, but translating their weights to our so-called product weights gamma j, they could show that such a condition is not sufficient for weak tractability. But this is just here the general weight condition rewritten for our product weights here. So this is at the moment not a proof that this is not sufficient. But in a more general context, also this gap remains. So a lot of work is still open here for the L infinity problem. You asked here about the algorithms also here for strong polynomial and polynomial tractability. The algorithm is again as for L2 approximation. And for the weak tractability notions, we used a certain spline algorithm that was introduced by Fred Hickenel and by Peter Kritzer, and which led us here to our characterizations of the weak tractability notions. Yeah, and what remains also open is, of course, the problem of general LP approximation for P strictly between 2 and infinity. Of course, L2 approximation is not harder than LP approximation for P bigger than 2, which in turn is not harder than L infinity approximation. So we get these relations here between the information complexities for L2, LP, and L infinity approximation, at least for the absolute error criterion. And this means, of course, that every sufficient condition for tractability for the L infinity approximation problem leads to sufficient conditions for the LP, for tractability of LP approximation. And the other way around, every necessary condition on tractability for the L2 approximation problem leads to a necessary condition for the tractability of the LP approximation problem. So in the first step, of course, one can take our results for L2 approximation and L infinity approximation, put this into a table and get first information about necessary and sufficient conditions for the general LP approximation problem. But unfortunately, these conditions are always far from each other. So there is always a big gap between sufficient and necessary conditions. So also here, a lot remains to be done in the future. So this, I would like to stop for today. Thank you.